lunch crowd right now, but for those of you who stayed, thanks for listening. I'm going to present to you in the next half hour all the recent progress in tests of the electroweak interactions at Hadron colliders. It includes the Tevatron and the LHC. And I've enlisted Joaquin Sorolla paintings to help illustrate things as we move along. The scope of my talk is as follows. We'll cover recent progress in W physics, including the W mass and its production asymmetry, Z and Drell-Yan cross-sections and angular distributions, Diboson physics and in relation with triple gauge couplings, and lastly, tribosons, vector boson scattering, and quartic gauge couplings. One thing I won't be covering is vector boson plus jet studies. That will be a part of Chiara's talk in the QCD summary tomorrow. There are two large stories going on in electroweak physics at colliders right now. One is the attempt to over-constrain the standard model via precision electroweak measurements. You know, for about the last 10 ICHEPs or so, people have shown a plot like this, which shows the relationship between the top mass, the W mass, and the Higgs mass. And you try and predict, say, what the Higgs mass is, knowing the other two. Or even before we discovered the top, we attempted to predict the top this way. And now that we've measured M top and M Higgs very precisely, we now have a global overconstraint, which has a very reasonable p-value of order 20%. But now we've essentially flipped the script in the sense that M top and M Higgs are so well known that the indirect constraints on MW and the weak mixing angle are now better than the direct measurements themselves. And so now they're chasing us instead of the other way around. And the question is, can WZ experiment catch up with them? Alternatively, at the energy frontier, the Run 1 dataset from the LHC is now providing us TeV scale tests of single and multiple electroweak boson production. ATLAS, for example, can observe Drell-Yan lepton pairs with masses up to 1500 GeV, or Z boson pairs up to 900 GeV. And similarly, very high momentum production in the WZ sector in trilepton events at CMS. And as we approach this TeV scale, it allows us to test electroweak symmetry breaking there directly to see if the Higgs plays an exclusive role there or not. Moving now to topics in W physics, the Tevatron is still the king of W mass measurements. CDF and D0 have the world's most precise measurements based on really only a fraction of their data, 20% and 50% respectively. And they have very nice templates modeling about 1 million Ws here, about 2 million Ws here. They also have very precise models of lepton momentum and missing energy. And based on that, they're able to estimate the W mass from a template fit. Now, the kinds of ingredients you need to do that to the desired accuracy is a precision lepton energy scale as good as 0.01% in some cases, as well as a 1% precision model of vector boson recoil. And they build this up from the copious control samples they've accumulated over the years. In the end, they get a precision from CDF of 19 MeV in the W mass, 23 from D0, compared to 33 from the LEP experiments. And putting that all together, you see a very nice consistency and a world average precision combining them of 15 MeV. Now keep in mind that the indirect constraint now is 11 MeV, so we could try and do better. Should we try and do better? Well, if you look at the error budget for these measurements, the biggest ones are statistical and PDFs. They haven't used up all their statistics, and with just a factor of 2 improvement in PDFs, perhaps using their own experimental measurements, for example, as I'll point out later, and then incremental improvement elsewhere, they believe the final Tevatron result can get all the way down to 9 MeV, and then this error bar here will be smaller than the indirect constraint here, which would be a worthy goal. Meanwhile, in Geneva, the LHC has long coveted to do the same thing. They have excellent detectors. They have tens of millions of W candidates, so that's not an issue. However, there's 3 problems they're going to have to solve before they get there. The biggest one is PDFs. You know, C-quarks and gluons play a much stronger role in W production at the LHC than they do at the Tevatron. And in order to get 10 MeV precision or better, we're going to have to know them at least twice as well as we currently do. So that involves some precise measurements of vector boson production. Momentum scale, well, I think we'll get to where the Tevatron is, but it takes a lot of work to understand things to the extent that they do, and that work has not yet been accomplished. And then lastly, the recoil model and missing energy. This is challenging in the LSC environment due to the presence of large pileup, which really spoils the missing energy resolution. However, if you ask a bunch of optimists how this might evolve, the ultimate goal could be as low as 5 MeV. but I think it's a pretty long road to get there. But one step along that road is improving PDFs via precise measurement of the charge asymmetry in W production. With the millions of events we have available, we can precisely measure the differential charge asymmetry as a function of lepton rapidity, and this probes the up to down quark valence PDF ratio as a function of parton X. There's a recent CMS measurement. They used a mere 20 million W candidates, and a very precise missing energy model here of W plus candidates here on the left and W minus candidates on the right, where you can see a clear preponderance of plus over minus. It's really just an artifact of the proton having more up quarks than down for the most part. And you can convert that into an asymmetry measurement of 0.1% precision as a function of lepton rapidity. And you can see from the size of these error bars and the size of the theory error bars that this has obvious constraining power for all the PDFs. D0 has also measured the W asymmetry recently. The Tevatron has really only exploited a fraction of their data until very recently. They have a 7 inverse femtobarn muon asymmetry measurement with very small error bars compared to pre-LHC PDFs. And they're also able to directly reconstruct the W rapidity using the electron and missing energy 4 vectors. And that will also have a good deal of constraining power compared to old PDFs. LHC also has a stake in this game. They have unique access to high lepton rapidity, all the way up to 4.5. And new for this conference, they presented a measurement based on 1 inverse femtobarn, which constrains the PDFs in an X range that's really inaccessible by all the other experiments. They have an overlap region with CMS and Atlas, however, and you can see from this bottom plot that they agree quite well in this region. So this is a very interesting complementary result from our LHCb colleagues. To see how this affects PDFs, CMS combined their W asymmetry measurement with Hera deep inelastic scattering to see how this would improve the D-valence quark, for example. And you can see at very low X with this blue error band that we are realizing quite a bit of improvement. Similarly, the Tevatron compared their W asymmetry constraints with one of the latest PDFs, NMPDF 2.3, which includes even some LHC data, and even taking that into account, you can see with their very small error bars, they are going to make a big improvement over that one. So hopefully, with these improvements, that'll set the stage for more precise electroweak measurements in both the W sector and the Z sector. So moving on to Z and Drell-Yan physics, there's been a lot of progress in the Drell-Yan cross-section at the LHC. Both CMS and Atlas have measured the 7 TeV cross-section as a function of mass, ranging from 15 all the way to 1,500 GeV and lepton pair mass. To give you an idea of the size of these samples, CMS and Atlas currently have more lepton pairs from Zs than the entire LEP plus SLD sample. So, 20 million, something like that, or that's per experiment. And so with that kind of precision, we can learn a great deal. And in fact, we obtain excellent agreement with next to next to leading order predictions over 10 decades in cross-section. Two of the things we've learned from this is that if you want to describe the low mass data accurately, next to leading order QCD corrections are important, as you can see from this Atlas and CMS comparison, which shows better agreement with next to leading order. Meanwhile, at the high mass stage, next to leading order electroweak and also photon-induced production of dilepton pairs is also important. In fact, if you want a precise measurement at the TeV scale of dilepton production, it's essential to understand what the PDF of the photon is. It's a new problem for us to deal with. A new measurement for this conference is an 8 TeV measurement of the Drell-Yan cross-section, where we also see excellent agreement with candidates all the way out to 2,000 GeV. And then CMS, combining their 8 TeV data with their 7 TeV data, construct a differential double ratio in the mass shape. This is measured for the first time, and since so many things cancel, you get a very precise QCD prediction. And the data seem to agree with it quite well at this point. It'll be interesting to construct this from the 13 TeV data once it becomes available next year. They've also studied other production properties, including the transverse momentum and rapidity of Z-boson candidates. Both Atlas has done this at 7 TeV, CMS at 8 TeV, and you can compare that with a number of generators which each have their strengths and weaknesses in various corners of phase space. You can see, for example, that ResBos does poorly at high boson PT, but that's because it doesn't have next to next leading order corrections, which would be necessary to describe that. Atlas has also compared their data with a bunch of different models, and again, what you see is next to next leading order does pretty good at high transverse momentum. Resummed Monte Carlos do pretty good at low momentum, and the parton-shower Monte Carlos do something in between. So one of the things we can learn from that and attempt to do is to tune the Monte Carlo so that you have at least one Monte Carlo model that agrees with our data quite well. Atlas has attempted this by creating a new tune for Pythia 8 and a next to leading order Poheg tune, and that gives you 1% agreement over the entire momentum spectra from about 1 GeV to 100 GeV. One of the applications in the electroweak sector of this data is to measure the weak mixing angle. In the dilepton center of mass, the lepton angle with respect to the axis of the quark momentum gives you an angular distribution that's sensitive to interference effects, most importantly, the vector-axial vector interference of the z at the z mass. And that gives you an odd cos theta term proportional to the weak mixing angle. And proton-antiproton, the quark axis direction can be well estimated since it's highly correlated with the proton direction. But in proton-proton collisions, we don't have access to that, and you can see that this actually dilutes, so we often make the wrong choice for the quark axis, and this dilutes the statistical power of the sample to do that. We nonetheless attempt to do so, and Atlas has a measurement based on their 7TV data. Looking here at the angular distribution of central forward electron pairs, you see a clear excess of forward over backward events, which you can convert into a forward-backward asymmetry as a function of mass, and then extract the weak mixing angle from a template fit. When they do so, they get something that's about 6 times worse than the world average and about 1.8 sigma lower. It's systematics dominated by PDF effects. I'll say a word about that later. Meanwhile, the Tevatron D0 has a new result of the forward backward asymmetry based on 10 inverse femtobarns. They don't really have the same limitations in PDFs and dilution that the LHC does, and they have a measurement that's only 3 times less precise than the world average. Now, when CDF comes in with a comparable measurement, and I fully expect them to, then the Tevatron combination will then be on the same footing as LEP and SLD. And so we won't talk about merely the LEP plus SLD combination any longer. That's something to look forward to. I was also pleased to hear that low energy experiments also plan to have a piece of action that's equivalent. At the LHC, the prospects are maybe a bit more pessimistic, and that's because the systematics are dominated by the PDF uncertainty. This has to improve basically by a factor of 5 or 10 in order to get down to an interesting precision. And it's hard to see how that's going to happen anytime soon. But in the end, what we're shooting for is a target of getting below 1 times 10 to the minus 4 in precision for the weak mixing angle so that we can start over-constraining again. Now moving on to triple gauge boson couplings. How do we test how gauge boson interact with one another? Well, the main paradigm is to use an effective field theory. For generic new physics effects at some high energy scale lambda, you can construct an operator product expansion, retain terms of the lowest dimensional order, in this case dimension 6, and append them with Wilson coefficients, which you attempt to measure. Before electroweak symmetry breaking, there's 5 such operators available that preserve gauge invariance. 3 of them are CP even and 2 of them are CP odd. And then you break electroweak symmetry and you get an effective Lagrangian that looks like this. It has triple gauge boson couplings, Higgs, VV couplings, and quartic interactions. And you expect to see WW gamma triplet interactions, WWZ, and 3 CP even coefficients describing them. And if there's any kind of anomalous behavior due to these operators, they'll manifest themselves as long tails in the kinematics of diboson production. So what do the data say? Well, the LHC now has thousands of high-purity trilepton WZ candidates, and there's no evidence of anomalies in the tail of the momenta. We also have tens of thousands of W gamma candidates. Here the picture is a little more complex because we don't have a full next-to-next leading order calculation available. But if we restrict ourselves to exclusive zero-jet production where those effects are reduced, we do get good agreement as a function of photon ET. But this is something to watch out for as the theory calculation improves. Z-gamma production, thousands of dilepton photon candidates, but with no significant excess over predictions, all the way out to the TeV scale. And MIS-ET photon production has been looked at as well. This turns out to give the best constraint on, in this case, dimension 8 neutral triple gauge couplings. ZZ production, hundreds of 4-lepton ZZ candidates, no anomalies in the shape or the rate, And hundreds of ZZ to 2L2 new candidates have also been seen in the 7 and 8 TeV data. WW production has been measured at 7 TeV by both experiments, and they both used the leading lepton PT distribution to constrain anomalous couplings. You see there's no evidence of anomalous lepton momenta in their data. An alternative way to do this is to look at semi-leptonic events. At low momentum, the signal to background is not so great. That's this blue sliver here. But as you go to higher and higher momenta, the signal to background is not so bad, and the superior branching fraction ends up giving you a superior triple gauge boson coupling constraint. And here's the world summary of how things are going. The best single LHC measurements in black and red are about as good as the LEP combination, or the Tevatron combination, where semi-leptonic is leading the way. Once we adopt the 8 TeV data into this plot, those will provide constraints that are about 2 or 3 times better. And then we won't talk so much about LEP2 anymore. What we will talk about are Higgs VV couplings, which are, in a dimension 6 framework, are correlated with these couplings and should also provide interesting constraints. In the end, we're essentially probing an energy scale in effective field theory of order 2 to 500 GeV for a coupling of order 1. In 2012, CMS was the first to measure the WW cross-section at 8 TeV. They showed this at ICHEP then, and they observed about a 20% excess over standard model predictions with about a 2 sigma excess in significance. For this conference, Atlas has a new result, which has a very similar conclusion, about a 20% excess with a 2 sigma significance. It's not statistical significance largely. These measurements are systematics dominated. So that's something to look out for. However, there's no evidence of any anomalies in the kinematic distributions for these events. And I hesitate to be enthusiastic about this only because not all of the data from run 1 is in, and the theory calculation is being actively studied, in particular the next to next leading order effects and resummation effects for jet vetoes, which are essential for these kinds of measurements. Finally, I'll talk about Electroweak Z+2 jet production. It turns out that one of the amplitudes for Z+2 jet production includes a triple gauge vector boson fusion diagram. And you can isolate this from QCD production by requiring a VBF topology for dijets, which includes a large invariant mass and a big rapidity gap. CMS attempted to exploit this with their 7 TeV data a year or two ago and found a 2.6 sigma evidence for such a thing. But now both experiments have looked at their 8 TeV data, and both of them are reporting 5 sigma evidence for this kind of process, where Atlas was the first to publish this. The cross-sections they observe are consistent with next to leading order predictions. And you can see from the Atlas data here that as you go higher and higher in dijet mass, you can only explain the data by introducing an electroweak component to the production. With these large data samples available now in this regime, you can do all sorts of tests on how generators behave in this area. You can study rapidity gaps, jet vetoes, and so on. So it'll be a very important engineering study for future measurements of vector boson fusion production and vector boson scattering. This summarizes all the Atlas diboson measurements. There's good agreement, modulo the exceptions I talked about earlier in W gamma and WW. And similarly for CMS, where you can see that we have 7 and 8 TeV measurements for all the heavy diboson modes. Finally, moving on to quartic gauge couplings. What happens when 4 of these guys get together? Well, in the standard model, it's certainly possible for this to happen. You can have 4 W couplings, 2 W2Z, 2 W2 gamma, 2 WZ gamma, and if you introduce a dimension 8 operator product expansion, then 19 new Lagrangian terms become available to you, including ones that correspond to neutral beyond the standard model coupling, such as 4Z. Experimentally, this is manifested as a triboson or vector boson scattering phenomena, and those phenomena are related in a very complex way to the underlying effective field theory. It's very complex phenomenology here. The first attempt to do this was to examine 2 photon production of W pairs at CMS. The idea here is that you can isolate this from ordinary WW production by the fact that there's essentially no underlying event to their creation. And so you look for a lepton pair pointing at nothing. And we have a couple such candidates. It's consistent with expectations. But that limit alone gave us a better limit on gauge couplings, 100 times better than LEP. So this was actually a big leap forward in that regime. They've also looked at triboson production in the WW gamma and WZ gamma channel. The idea here is to look for anomalous high PT photon tail in the data. We don't observe it, and we got the first limits ever on several quartic gauge couplings, especially in this 2WZ gamma sector. Now for my last topic, I'm going to cover WW scattering at the LHC. So this is one of the reasons why the LHC was built, and it answers an important question, which is, the Higgs is believed to be essential to preserve vector boson scattering cross-section unitarity when you consider the scattering of two longitudinal gauge bosons. There's a subtle fine-tuning balance here between all these diagrams to control the growth of this cross-section as a function of S. Experimentally, an attractive topology is to look for same-sign WW vector boson production in association with two jets. And then that gives you access to an interference between these three diagrams here involving boson exchange, Higgs exchange, and a quartic coupling. Any kind of anomalous behavior here in the differential cross-section, say, would indicate either an extended gauge sector or new particles or some kind of effective field theory leaking down. So, well, I guess this is Valencia, so I'll go there. This is the holy grail of electroweak physics measurements at the LHC. And we're very excited to get on board with this, with the Run 1 data. So the 8 TV data have been looked at by both CMS and ATLAS for these same sign WW plus 2-jet events. And what ATLAS observes is, as they increase the dijet mass above about 500 GeV or so, and then restrict themselves to dijet events that are massive and with a high rapidity gap, they see an excess in this blue events, over the backgrounds, and at a rate that more or less corresponds to standard model expectations. 34 observed versus 30 predicted. This gives you a cross-section in their vector boson scattering enriched region that's consistent with standard model predictions. It's 3.6 sigma significance. And it's the first evidence for vector boson scattering at the LHC, so this is quite a milestone in our program. Limits were obtained on anomalous quartic gauge couplings in a unitarized model that corresponds to an energy scale of roughly 650 GeV for couplings of order 1. This is what one of their events looks like. Same sign muons, two jets back to back, very massive, very large rapidity separation. CMS has presented a similar measurement using a similar strategy, although a somewhat tighter working point, but very similar sensitivity expected for vector boson scattering. They observed 12 events and expected 9, and this corresponds to a 2 sigma excess coming from vector boson scattering processes, with no funny distributions in either the dilepton or dijet mass. And this gives a cross-section consistent with next to leading order calculations. They also use that to constrain quartic gauge couplings, and you can also use it to constrain the doubly charged Higgs sector. In this George Matusek triplet model, they now have limits as low as 20 femtobarns on the cross-section. So the future prospects for vector boson scattering are great, looking ahead to Run 2. We expect several modes are expected to be seen, including WZ, maybe opposite sign WW, and others. And there's even the potential with the phase 1 data alone to identify at the 5 sigma level some kind of anomalous operators at the 1 TV scale. So that's definitely something to look forward to for ICHEP 2016. To summarize, W and Z physics, using tens of millions of events now, are giving ultra-precise tests of PDFs and quantum field theory calculations. And this is in preparation for the final assault on further constraining the precision electroweak sector. The LHC is now the leading laboratory for understanding gauge boson self-interactions with diboson data approaching the TeV scale. And the great new news, the vector boson scattering era is upon us. And now we're posed to directly test electroweak symmetry breaking in the future. Thank you very much.
Thanks for this illuminating wrap-up, and we do have time for a couple of questions.
Jeff, as you mentioned that W mass measurement is not limited by statistics at the LHC because you have large
Yes.
data sets, but by systematics, and probably pileup is among them because measuring sub-GV accuracy, missing ET for 100 interactions per crossing is challenging.
Yeah.
Did you consider running for like relatively brief period of time, like a month at a lower luminosity in order to collect data for this measurement?
There have been, proposals like that, but, in order to collect, say, many inverse femtobarns at that low of a pileup would take more than a month. It would take a long time. And so I think we'd have to be highly motivated to want to go in that direction. And I don't think we're so motivated right now. We'd much rather do searches.
About this cross-section of the WW,
Yes.
I think we don't think anymore it's a statistical fluctuation in one experiment at one energy. It's seen everywhere, right? And,
Yeah.
and if you say that WZ is not hurting us, then the idea that it's a PDF is not very appealing either. So I don't share your, let's say, relatively light-hearted comment about that.
Well, I mean, if you kind of closely inspect how the cross-section is estimated, you see that there's room for at least another 4 picobarns, say, from higher order effects or other things that aren't included. That turns 2 sigma into 1.5 sigma, roughly. And maybe then it's not so exciting. Also, as I said, not all the data is in. And when it is, that might be more decisive. I would hold out for all the results to come in before coming to any conclusion.
You blame it on missing calculations.
It could be a cocktail of, the systematics are 1 sigma off than we think they are. It could be, 4 picobarns or more shift in the cross-section due to higher order effects. There's also these jet vetoes, which of course give you some difficult resumming to do.
Not present in WZ.
That's right, that's right.
Okay.
So that's a difference between WW and WZ that's important, in fact.
Any other urgent questions? I don't see anybody. So let's thank the speaker again.